Okay. Right, so okay, I think we can start. Well, the title, this is a course I'll be giving, and right, the title is a bit of random. It's about real-time systems and related stuff. Okay, so let me first introduce the course. Well, first of all, it's a course intended for PhD students. I'm not using the screen. I apologize if here is a problem. Once in a while I have to draw, so I prefer. Yeah, maybe that line is a bit. Yeah, but from there, maybe from the projector point, yeah, maybe. Yeah. Okay, so basically, yeah, course for PhD. What does it mean? It means it's kind of experimental. So sometimes I think, wow, look, nice, be nice to tell this, and I put in a slide. Okay. Then it means it's not really fully validated in the sense that it's nothing wrong. Well, there may be mistakes like typos and stuff, but I prefer just to say something, and maybe if you don't believe it, no, this is wrong. So I like to do it like in an interactive way. So, right, I'm trying also to give an overview of a research area, which is quite broad. And I will expose quickly many topics. So it's up to you to stop me, to slow me down. Enrico, what did you say here? What did you say there? So, I mean, if you don't understand, it's not, well, it's my problem. It's also your problem because you didn't stop me. Okay? So please raise the hand. Feel free to interrupt me anytime. Right. So what else? Yes. I mean, for those of you who have to give the exam, this is worth 1 credit. Okay. And right, the exam is given. Well, there's going to be 6 classes, like Thursday, Monday, Thursday. Then there is a homework assigned here that you have to do it at home by yourself, and then you have to submit it to me by this deadline, okay? Which is probably the day before of the class after. So make it Thursday today, Monday, Thursday. Then I skip a Monday because there is the June the 2nd celebration on Monday. We go to the other Thursday. So in this week, I mean, the homework are due. Well, are due. You have to do on the other Thursday. Then Thursday, Monday, Thursday again. Anyway, so okay. Well, when no reference is provided, Wikipedia is fine. So I mean, if you don't know about round robin, you just Google round robin and find it. So I'm not explaining any concept. With the material, right, my slides, I will, now I will present, I'll see how far I can go, and then I will finalize the slides. I will put on this Didactive website, which I hope, maybe you have no access here. You can just send me an email, I can invite you to join here. Right? And also your notes and papers on the web, the material is whatever you want. Okay? Yes, as I was saying, yes, there may be mistakes, typos. Then it's just let me know if you at some point I think something, I say something else, and so just interrupt. Okay, scheduling problems. What are scheduling problems? So, what are the basic elements, the basic ingredients of a scheduling problem? Well, a scheduling problem, at least in the way that I formulated, we have a set of tasks. Okay, I indicate the set of tasks with this n, and the tasks are n. And since they are a finite set, we can just identify the task with just the number into the index of the task, right? And we also have a set of n machines. And the machines are the guys who can do the job, who can do something, okay? And I mean, now from this point, also about, I'm not entering into too much of details of, I'll provide a bit more detail later on, but I'm taking a big overview. I mean, I'm not entering into the details of how the machine is done, what type of processor resource work. I mean, what are the characteristics? Then there are constraints. Example of constraints are, let's say, affinities, deadline, mutual exclusion, So you may want one task always execute on some machine, or you may have some constraints. Then we have a time set, which is the time over which you are scheduling tasks over machines. Okay, and the time set may be often maybe vary. Typically, is either the natural number or it is the real half-line from 0 and the positive number, the non-negative numbers. And then we have a scheduling algorithm, which provides a schedule. And I will explain later what a schedule is, in this context, which is compatible with the constraints. Okay, so these are just the big objects that we will be talking about. Okay, so task. What are the characteristics of a task? Well, a task is characterized by the amount of work it has to do. By the fact it may be recurrent or non recurrent. Typically, we use this word to this adjective to say task, right? In this case, it is sometimes called recurrent. Or if the task is just one shot, so you have to do something, you do it, and once you're done, it's gone. Okay, but anyway, these terminology are not. One problem of this research area is that terminologies is not well established. So and even notation is not well established. So now I'm using these words like recurrent, recurrent. There is no real consensus about what terms to use for what. And right, task may be like online or offline, meaning that do we know in advance before building the schedule the characteristics of the task? In this case, tasks are known like offline, so we know offline the parameters, the characteristics. Or do we find out online what are the values, the computation time, the load, whatever? Is also another characteristic. Also, this is the type of the task may be sequential or parallelizable or parallel if you want. So meaning that if I give to this task more than one machine, is this task capable to do it or to take advantage of these machines or not? If not, then yes.
What is the difference between parallel and parallelizable?
I was reading these slides and I said, but why did that more than one machine? I think that the point with parallelizable is that the difference is that parallel, I think in the way I interpret it here, is that it has to be parallel, right? Parallelizable, it means that it may be parallel. So you have like tasks like this with no dependency. This is parallelizable because you can do it also like this. If it's parallel, you really have to execute it this way. Like actually, yes, it triggers me. Now I remember why I wrote it, because we have this model called like gang scheduling. In the gang scheduling, you have this task model where you are executing in parallel, and the model requires that parallelism. Okay, it's not a parallel that you can use or not. So it's really parallel in this sense. And parallelizable, on the other hand, is like a thread-based. So you have threads, and if you give them a parallel machine, then it can run in parallel. If you give only one sequential machine, it will run in a sequence. Okay. So now we denote the work request of a task tau I by a function. It is Ri of t. Okay, Ri of t basically is right the amount of work that is the maximum amount of work that is required in any interval of time t. Okay, that's Ri of t. So it's kind of increasing with t. So if, for example, just to give you like an example, oh no, right now I was wrong. Sorry. Is when the request comes. So it's the amount of request that arrives. In fact, let's say if the task is job based, so if a task is composed by jobs that arrives at some point, so let's say it's composed by jobs which arrives at instance Aij, and each job requires Cij computation time, then you call this function Ri of t, which is just a sum of Dirac delta translated at all points. If you just do I hope there is something to draw. Let's see. Like here. Good. So, for example, so let's say in the example before, I assume that here I have a request at time A, I1, I have a request of C, I1. Here I have a smaller request, A, I2, C, I2. Here a big request, and so on and so forth. So these are the type, and these are Dirac delta, okay? I'm using Dirac delta because later I'm going to integrate this, okay? So we use this, and this is, you may think of also a continuous model. If it's a continuous model, then you may have something like this, right? I mean, if the time are very small, close to each other, and the amount of the value of the delta is very, very little, and the requests are really, really many, you can approximate them as a kind of density of requests. So it's the same as we do with the math. But if you have like discrete requests, I mean, if the granularity of requests is bigger, then you have to use this model. Okay.
Basically, delta is the number of requests arrived.
No, delta no. Delta is a Dirac delta.
Is a what?
Dirac delta is a function. Yeah. In analysis, the Dirac delta is this. I mean, it's not a number; it's a function.
Okay.
So delta of 0. So delta of 0, delta t basically. Delta t is a function which basically is hard to define, but the only important of delta t is that if you do the integral between a and b of delta t dt, then this integral is 1 if a less equal than 0 and b larger than 0. 0 otherwise.
Okay.
Basically, it's a function that you can think as, or if you want to, if you can think of delta t as the limit of a rectangle with an area 1, where you make, let's say, of size, if you want, minus t half, and let's say t half here, and here you have 1 over t. So that makes the area 1, and then you make the limit of t to 0. You have this rectangle that shrinks here, but it gets very, very high, and that's the Dirac delta. And then when you write here, basically I'm translating a Dirac delta at this point, and I'm multiplying by this. So basically, right here, if you translate, basically, if you're translating this point, then this integral is non-zero only when the point where the Dirac delta is into the interval. And if you multiply by a constant, then the area, instead of 1, is the value of the constant you're multiplying with. Okay? Okay. Yes, I also, let me erase what I can erase. Okay. I wrote this because maybe it's also nice to notice that if we may use a negative Cij to mean that at some point we suppress some work. So we have a request not to work anymore. So negative means that it's kind of negative work. So you can see it as we have some work that is we don't have to do anymore, or something like that. But it's just for fun actually. Right. We also denote the pending work of a task by Wi of t. Wi of t is the amount of so basically here we have requests that are coming, and then we have machines that are able to execute. And then some work among the requests is the work that we may have is pending. Like it's in the queue, it's in the buffer, it's something is pending. Okay. Okay. So we denote the work pending at time t. We denote it by WIOT. Okay. And right. So I mean, kind of basic principle that bind the pending work and the request, if you want, is that work at some time, it's time t1. So if we have here time t1 and here time t0, the pending work here minus the pending work here cannot be larger than the request here. Let's see what I'm saying.
The request between T0.
Yeah, the request between T0 and T1. Yes, this is some basic. Yeah, good. Yeah, so basically here, right? So here there cannot be more pending work than the one that I have accumulated. Let's say if I do nothing, then we have the equality. So if I do nothing, I have the equality. So here I cannot have more than what was pending here and what has been requested here. That's why it's pending. Okay. Okay. What is a machine? Well, a machine is something that can do tasks. Okay. It may be like a type. I mean, depending on what task, it can be like a coffee machine making coffee, or it can be like a CPU. It may have a speed, which may be time varying or demand varying. So the rate at which the machine is working. Okay. Right. Operating modes. Yeah. Variable speed, whatever. And it could be characterized by the availability of some resource. So basically, the machine, on one machine, I may have like on a source. So it may be characterized by some characteristics. Okay. And constraints. Okay. Well, constraints may be of many types. Here, just list some of them. Maybe precedence constraint. So this task can only start only after this other task. Or deadline. So this task must complete by the deadline. Affinity to machines. Okay, this task can only run on this machine or on this set of machines. This is called affinity. We adopt this terminology from Linux, so maybe it's even used anywhere else. And mutual exclusion, right? So this portion of tasks cannot execute at the same time. Okay, so this is mutual exclusion. These are I see this as the constraints. Okay, now what is a schedule? Now, well, a schedule basically is a function that goes from the Cartesian product of machines and time to the set of tasks union 0, where 0 is a sort of special task that it is denoting idle. Okay, so when you have 0 is idle. Okay, and this schedule has to be compatible with the constraints that are in C. Let me just make a very simple example. A way that we can do. So basically, we can see it a very common way to draw it is by a plot. Let's say if we have machines 1, 2, M, and here you have time, and so on. Okay, and then we can use, let's say, a color to say what task is executing where. Let's say here task, yeah, the task is executing here, 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 here. It is the same task. And now here, here, here. Okay, so this is really a function from the Cartesian product of time and machines to tasks. Okay, this is really a quite convenient way to see it. Okay, so and we represent the value of these functions on this axis, let's say on the task axis. So very often, since it's discrete, we often represent it like colors, I mean, of patterns or numbers, or this is just a way to represent. And 0 then is here when you have nothing, it's 0. This is a common way to represent a schedule. Is it clear again? Right. Okay, so we have, of course, if m is equal to 1, if the number of machines is equal to 1, then here there is a set that is just a singleton. So, I mean, there is no dependency. So it's just a function from time to the set of tasks. Simple. And of course, yeah, the interpretation. Yeah, the interpretation is the one that I just told you before. Right? So Sk of t, if Sk of t is equal to I, what does it mean? It means that the machine k is assigned to the I task at time t. Okay. If it's 0, then it's not assigned to any task. It's idle. Okay, this definition of schedule, yes, of course. It implies that at every instant, each machine is assigned to at most one task. Okay. However, at every instant, each task may be assigned to more than one machine. Okay. Because if you remember the draw before, I can have at the same time all the machines could have the same value, the same task. So this model is general enough. It includes also parallel tasks. It includes everything. But soon I will lose this generality, and I will focus on a more. I have just 12 hours, so I cannot treat everything. But then, this model so far is still general. Example of a schedule. Okay. Now, quite interesting concept is this. Right, is the inverse image of a task, right? So S minus 1 of I, which is basically all the pairs in the Cartesian product which have value I. This is just, the schedule of the task. Okay? Nothing surprising. Yes, here I wrote a note for myself. Draw a schedule. Okay, I did it already. Now, well, let's see how we can play with the definitions to define some concept that hopefully you are familiar with. We can say that the task I is sequential if what? Well, for all pairs kt and k prime t prime into the schedule of the task, if t is equal to t prime, implies that k is equal to k prime. Is it clear? It is sequential. For all pairs that are into the schedule, so imagine what is S minus 1 of I. S minus 1 of I is this, right? Let's say I have 3 machines. 1, 2, 3. And this task is something like this. Okay. Is it true that for all pairs into this set, this property holds? No. Because I'm requesting that for all pairs, so among these pairs, I also have this pair, a pair here and a pair here. These are 2 pairs with let's say, t equal to t prime. And here I have k equal to 2 and k equal to 3. Here I'm saying that, in fact, for all pairs in the schedule, like this one, t equal to t prime, as in this case. However, k is not equal to k prime, because they're different. Okay? In fact, this task is not sequential, because it is executing in parallel. If you have a sequential task, in fact, is really without this part. Okay? And that basically means that if you have for any pair, pair, I mean here, of course, this pair may be the same, right? For any way you pick two pairs, if the t is equal, is the same, then also the k has to be the same. And that's the sequential. Okay. Right. So let's see the second one. And the schedule S is partition if for all pairs. So the task is partition if for all tasks, for all pairs in the schedule of a task, for all pairs, then k equal to k prime. So anytime a task is executed, k is equal to k prime. Wherever it is, k equal to k prime. Okay, this is partition. Clear? Questions? Okay. Now, law of conservation of property. This is something that it is quite natural, but yeah, it's good to have it. It's the same as what I was saying before, right? That the pending work at T0, at T1, sorry, is equal to the pending work at T0 minus what I've executed plus what I've requested. Okay. I mean, maybe the integral is confusing, but it's exactly this. Let me now, how can we write this? This is a kind of tricky way. So this is the amount, it is a scheduled resource of two tasks I between T0 and T1. I have this kind of complicated expression, but which is used concept that you should know. But first of all, let me I denote by sk of t, the speed of processor k at time t. Okay. So what is this sum? The sum is over all the pairs kt that belongs to the schedule. Okay, so I integrate t, and I make the sum, basically the sum over all the k, right? So let's make an example.
Enrico.
Yeah.
Excuse me. Just K is for the machines and T is for the time, right?
Yes.
So, but you always draw the time on the.
Ah, yes, right. Yeah, I do.
Okay, so the pair is not actually KT but TK.
Yeah, it's just an order. If you want, yeah, but that's just a drawing.
No,
I can draw.
No.
If you want, I can.
It's absolutely sure because.
This is. I agree.
For me,
I agree. I mean, so often the first coordinates is like the x-axis and the second is the y-axis.
It's just to be sure.
I can go up.
No. But,
okay. You're right. Yeah. If it has to clarify, it's good.
Okay.
It's good to. Yeah. T runs over here, and K runs over here. Okay. Okay. So again, so S minus 1 of I is this, is the schedule. So what I'm doing here, so for it, I'm doing the integral over t. So let's say for this value of t, I'm doing what are the pairs kt? Well, there is only this pair. So basically, I'm doing the summation of the speed of this processor at this time. So as I move on, here at some point I get another processor. So here basically I do the summation of the speed of this and plus the speed of this. Okay, and then here I have nothing. Here I do this way. And basically, of this kind of sum of speeds, I do the integral from t0 to t. Okay? And this is the amount let's say I have some T0 here and some T1 here. Basically, let's say in the simple case, if you have unitary speed, basically this stuff is just a complicated way to write to denote this area. Okay? If you have variable speed, then you have to do the integral of the speed. Okay, just to complicate a bit, this is just, the point is that this model, this formulation allows a very broad task model, machine model. And, I like at the beginning to provide the formulas for a very general model. And maybe in the next slide I will specify immediately, but then I like at this point to be as general as possible. Okay, right, scheduling algorithms. Scheduling algorithms, well, the goal of the algorithm is to find a schedule such that what? The constraints are met, and some target function is minimized or maximized, let's say the response time of some task, the lateness, the minute span. So you want the scheduling algorithm typically is driven or fairness, if you some property. Okay. What are typical characteristics of a scheduling algorithm? The scheduling algorithm may be work conserving. That means that no machine is left idle if there is a pending task. So I defined before the pending work by Wi of t, right? So if there is some Wi of t different than 0, so greater than 0, that we have pending work for some task, we cannot leave the machine idle. Okay, so a work conserving is an algorithm that always execute when there is something to execute. Then another characteristic is if the algorithm is preemptive or not preemptive. Preemptive means if I can interrupt a task while executing to execute another task or not. Okay. Then the algorithm has a time complexity. How long does it take to take a scheduling decision to compute the schedule? That's also the time complexity of the algorithm. It may, well, in reality, it's never clairvoyant, but sometimes we use clairvoyant algorithm to compare against. So we say, I can assume an algorithm to be clairvoyant, which takes decision also based on the future. But of course, it's something that you cannot do. But as a term of comparison, you
basically assume that the clairvoyant algorithm is optimal.
No, it knows everything. Then what you do, knows the future. Then if you take the future and you take wrong decision, it's the problem of the algorithm. Okay. Clairvoyant is just knowing the future. Yeah, just a sample of scheduling algorithms. Well, FIFO is first in, first out. Well, you schedule tasks as they arrive. As one task whenever it arrives, then you schedule it as soon as possible. Round robin, you divide the time in time slices, and you give time in rounds to all tasks. Shortest job first. Any preemptive version is shortest remaining time first. You just give higher priority to the task with shorter job. Earliest deadline first. Assign priority according to the absolute deadline. Then you have something probably you know. Least laxity first, which assign priority according to the smallest laxity. The laxity is the remaining time from so basically if you have to complete the job by a deadline and you are at time t now, okay, and you have to at time t you still have to compute c prime amount of time. Then, well, this should be, I use this notation W of t. Let me correct. It's the pending work. Okay, right. So here, your sense was the laxity, right? So if here you have to still to compute this amount of time, basically d minus t is this interval, minus c prime is this well, no, minus this, then is this is the laxity. The lax is how much slack you have before reaching the deadline, and least laxity first schedule jobs according to the one which has the smallest, okay? Least first. And then fixed priority, you just set priorities to tasks, and then whenever the first one is ready, you run it, the second one, and the third one, and so on. Okay? Okay.
So, how can you schedule online with least laxity? So you should predict the future.
You should least laxity first assumes that you know the computation time
Okay.
and the deadline.
So,
Okay.
So
you know when the task.
you know when it has a deadline, and you assume.
But you should also know when the task arrives.
Well, online you know that when the task arrives. No, you don't know. I mean, the laxity is the amount of time that is left. I mean, assume that now you execute always from when you finish to the deadline. So it's the slack that you have to execute that task. I mean, the time that you can waste.
But for sporadic tasks.
No, it's for the tasks in the ready queue, not for
Okay.
the
Okay.
Yeah.
I got it.
Okay. Then a common concept here is the difference between feasibility and schedulability. Basically, we say that a task set N is feasible if it exists any schedule which satisfies the constraint, while we say that a task N is schedulable by an algorithm A if A can produce a schedule which satisfies the constraints. Okay? And the constraint of C, let's take. Okay. And of course, schedulability implies feasibility, because if you have a scheduling algorithm which can produce a feasible schedule, then a feasible schedule exists. Okay, now, I mean, the general part is somehow gone, and we enter a bit more into real time here. I'm assuming a very super simple task model. Okay, task and sequential. I mean, if you want to see sequential with that definition of schedule, yes, you can. And we denote task by tau I. Task I typically is by tau I. Tasks are recurrent and activated sporadically. Basically, so tasks are activated over time. Activated sporadically with the minimum interval time or period, if you want, of Ti. So Ti is the minimum separation between two consecutive activations. And we call typically job the amount of work that has to be computed at each activation of task. Okay? And all jobs belonging to the same task have the same execution requirement CI. So now, if just to use the same notation that I was using before, if Aij is the sequence of activations, okay, when the task is activated, then basically the minimum interruptible time constraint implies this, that the separation between the j+1 activation and the j activation is greater or equal to Ti, because I mean this is by definition. Okay. And then the amount, the request is exactly this. So it's just the Dirac delta translated at all the activations. Okay. Each one multiplied by the computation time. Okay. Right. So we often use also the term task utilization to denote this ratio, the ratio between computation time and period. Okay. Are you all familiar with this notation? Fabio?
I'm not familiar, but I can understand.
Okay, that's fine. That's not, I mean, yeah, before. Okay, it's something that you will know or not. Okay, nice. What about the deadline? All jobs belong to a task. Now I have a deadline of DI, relative deadline, and then the absolute deadline of the J job is denoted by Dij, and is set to the arrival plus the relative deadline. Very simple. Okay. So just to draw, something that probably you know, but it's just to do something. So basically we have these arrows up, where the separation is larger or equal than Ti. Okay, and then we typically use the arrow going down for a delta. So basically, there's a delta here, there's a delta here, it's there. Okay. 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 Some other terminology that is kind of consolidated, some kind of classic. So if the delta is equal to the period, which means that you always want to ensure that when a job complete, when a job is activated, the previous one is finished. Okay. Yes. If then we call it implicit deadline. If the deadline is less or equal than the period, that's called constrained deadline. If the deadline can be anything, larger, I mean not necessarily larger, equal or smaller, anything, okay, then it's called arbitrary. And right, so what does it mean to schedulability of task tau I? It means, I mean, using this notation that the time that you, okay, let's see this over time. Easy. So you have activation, AJ. I mean, this formula I wrote it yesterday, so it may be wrong. So correct me if it's wrong, if you're not convinced. Right. So what I'm saying, what do I mean that we, to schedule that this task is schedulable? If for all its job, the amount Si, Ij, Dij is the amount of resource that the machine allocates here, okay, between Aij and Dij. So this amount of resource has to be larger or equal than the pending work here, because it may happen that here the task I has some pending work, plus the computation time of the task. Okay, so here
it has pending work if it misses the
so it is deadline larger than or it has,
so it's schedulability for the specific job, not schedulability at large.
for all, no, but wait a second. If the deadline of the previous one is here, if you have arbitrary deadline, here you may have.
I was thinking
about
implicit.
Yeah, if you have implicit or constrained deadline, the pending job is supposed from this exactly from this for all condition by induction you can prove that it has to be right. Okay.
But you have a pending work at time Aij, and but we suppose the deadline is a later deadline than the deadline of job J.
Oh. So if there is a job with earlier deadline that falls in here.
You mean if the job J arrives
Earlier?
after its deadline?
No, what he's saying is that if there is a job arriving here with a deadline here.
No. Suppose the job has arrived earlier.
The job has arrived earlier.
And no, this is at a job level, right?
It's for all J. If a job has arrived earlier, it's not complete, then here we have pending work. This is not zero, okay?
Okay, yeah. Sorry.
If you have pending work, if this job is not complete, then it has a pending work. Okay? I don't know, it may be wrong, but you know, this is. If you find it's wrong, I mean,
who cares?
it's experimental, right? I'm not writing a paper, right? I Now,
Maybe from completion's point of view, it's better to use WI using some index to.
yeah, I think I did.
Yeah.
Yes,
That's the
yes,
problem.
yes.
Because W
It
means
was WI, it was WI, but now it's WI. Yeah. Thank you. Okay. I mean, writing wrong things is also good to stimulate the discussion, right? Otherwise, it's boring, right? So the more mistakes, the better. Okay, machine model. Machine model, yes, we have this single processor or multiprocessor with them core or whatever. And quite obviously, a necessary condition for feasibility is that the sum of all of the, your I is missing. One is missing. Is that the sum of all utilization is less than or equal to M. Otherwise, it's overloaded. So basically, you have more work to do than the number of. But here in the course, we focus on single processor. So all the fancy multiprocessor, we just don't care about that. So if you want a multiprocessor, you can leave. I'm fine. I don't take it personal. So it's just single processor. Okay, now
there is an index in the summation that.
Yeah, took note.
Oh.
I is missing. Is missing one here.
Okay, so.
Right. So fixed priority. Now we are entering. We are specifying a bit the story. So we are entering into the study of fixed priority. Okay. In fixed priorities, tasks are sorted in decreasing priority, meaning this is quite consolidated habit. The tau 1 is the highest priority one, and tau n is the lowest priority one. Okay? Yes, draw an example of how fixed priority. Yeah, draw an example.
It was a reminder for you.
Yes. Oh, yes.
Mandatory. Drawing session.
Okay.
No.
Thank you. Right. The classic example, 4, 8, 12. 6, 12. So let's say we have a period of 4, computation time of 2, and computation time of 2, period of 6. Okay. No, we don't see fixed priority here. Oh, well, it doesn't matter. So basically, computation time period 2, 4, computation time period 2, 6. This is tau 1, tau 2, high priority, low priority. But easy. I mean, even the way to draw the schedule, you first look at the first guy and you draw its schedule. Because nobody is going to affect this guy. Then you take a look at what of the time it is left available and you draw the second guy. So here is scenario 2. Here this guy fits exactly here. It fits here. Done. Done. Okay, easy. What is the best priority assignment? Yes. Right. We have this quite well-known result by Llewellyn, which says that if the deadlines are equal to periods, then rate monotonic is optimal. Rate monotonic means to assign priorities based on inversely proportional to the period. Okay, so high priority to small period, and so on. Okay. What does it mean optimal? It's always good to know what it means optimal. If some priority assignment, if any priority assignment can schedule the tasks, then rate monotonic can also schedule the tasks. Okay, that's also optimal in those terms. If in the constrained deadline case, deadline monotonic is optimal. Okay, which does the same story of.
That means optimal with respect to other fixed priority.
With respect to other priority assignment. If
no other priority assignment means that I cannot use a dynamic priority assignment.
Oh no, here we are
Or a
in the
fixed
cost.
priority.
Here in the cost, I got fixed priority assignment. If some fixed priority, yeah, some priority assignment, that's
Ci stava per pelo.
No, beh. If any fixed period sun, right? Any fixed period sun, che schedule. The task is very much, okay? Okay. In the arbitrary deadline case, the optimal period assignment is not so straightforward. And, well, it's complicated. I don't care. Okay? Utilization per bound. Right. Lewin Leland proved also a very this result in this paper, which is very popular. I just checked. I mean, I checked 2 years ago about how many citations does this paper have. Let's see. Let's check now. Now let's check on the how many citations does it do. So let's see. So it was 7,914 in October 12. Now I'm curious.
Are you the guy that say, sorry, Professor, the upper bound is wrong?
Huh? No, this bound is wrong.
Yes.
This bound is not wrong. No, I'm not the guy who said that this bound is wrong.
Okay, but that you can improve.
Yeah, you can improve, but doing not a linear bound. So it's 9,000. So it's increased 1,000 a year, basically. 1,000 citation a year. So it's quite a lot. No, a bit less than a year. This was 12.
Probably the citation.
So it's not 2 years. It was a
No, I mean after the bracket.
Yes, because BibTeX is not working. No, I know. I mean, because I use these on the nose. I mean, the references in the slides are not. Okay. What does it mean? Okay, what is this very famous result? This famous result says this, that, okay, so if deadlines are equal to periods, okay, then, and if this condition holds, so the total utilization is less or equal than this value, and which is a value is always less than 1, and if n is equal to 1, what was the value of when n is equal to 1? What's the value of this when n is equal to 1?
About 6, 8, something like that.
When n is equal to 1,
N is
0.1? 0.
when n is equal to 1,
Yeah,
the square to the 1 is 1. So 1, 2 minus 1, 1, 1. Okay? With 2 is something. Okay, so then if this is true, then the task is scheduled by rate 100. This is called utilization upper bound. If n goes to infinity, this is a quite nice limit to do. If you want to do a good exercise, then you do this limit to remember a bit of math. It may be an exercise for you for the next to compute the limit. Okay. So and then the limit is log 2. It is approximately this value. Right. So is it typed? So is there any non-schedulable task set with this? No, is there any schedulable? No, is there any? Of course, there are no schedulable. Is there any schedulable? Is there any schedule? The question, interesting question, is if there is. I don't know. If it's tight, no, okay, no. Okay. No, it's okay.
I want to remember you that you are now streaming worldwide.
Ok, che cazzo ne cioè adesso stai registrando?
Santi sì.
Sì, proprio, no, chi te favoreggiava queste cose. Vabbè, worldwide. Okay. But the people knows me anyway, so I'm not hiding. So, what's the point of tightness? Right. So here, comment for me. Draw the example. Let me draw in the space of utilization of two variables, u1, u2. Okay. The necessary condition of sum of ui less than or equal to 1, which in two cases it's u1 plus u2 less than or equal to 1, is this, right? So this is necessary. There cannot be anything scheduled here. Liu-Leland says this. Look here at, well, 2 is 2 square root of 2 minus 1. Okay, here, which is, well, I will compute later, 1.41 minus 1, kind of 0.82 if you want, approximately. Here, yes. Here, no. Here, well, first of all, is the utilization upper bound tight? Meaning that can I move this line up, I mean this way, without including any non-schedulable? No, because as soon as you move this a bit, you will find some non-schedulable task. Okay? So the Liu-Leland bound is tight in this sense. But still, about this area, we don't know. There's still a lot of uncertainty here. So there is this hyperbolic bound. The hyperbolic bound is basically this, is written in this way. And actually, it improves quite a bit because it says, in two variables, it says this, that this condition in two variables is 1 plus 1 u1, 1 plus u2 less than or equal to 2, which then you can write as 1 plus u2 less than or equal to 2 over 1 plus u1, or if you want, u2 less than or equal to 2, 1 plus u1 minus 1, which is 1 plus u1. Okay, so basically this curve is 1 minus u1, 1 plus u1, maybe, if I did no mistake. It goes through 1, ci metto 1, 1 fa 0, vabbè, ci metto 0, fa 1, it's okay, alright? Okay, and so it touches the Liu-Leland bound here, but then it also goes through these points which are clearly feasible. I mean, these points are quite obviously feasible, right? These points correspond to the case where basically you have one task only, because you have utilization u1 equal to 1 and u2 equal to 0, so it's only u1. So it's good to, I mean, the point that the Liu-Leland bound was far away from this point was not so right. So at least including easy schedulable tasks is nice. And that's, I mean, at least the hyperbolic bound includes these extreme points. Okay? So basically, right, so now we have these as also feasible, schedulable, but still here we don't know. Okay? We don't know. I was wondering when to make a break. Yeah, maybe now we can take a break. We can take a break. You take a 5 minutes only, yeah, because yeah, it took a bit too long. Okay, 5 minutes.
Su you.
Streaming, fa anche gli stacci? Sì. Ma anche gli stacci?
L'hai dato